Let's go. Today's called scientific notation, which isn't too hard. It probably will get a bit trickier when you get towards the end of the exercise where you combined your indices or index laws. It's really only index law 1 and 2. But let's start here getting to make sure that you know how to use scientific notation. Here it is. Let's fill in a couple of blanks with the colorful pen that was kindly suggested. Scientific notation is useful when working with very... Can we read that? Yeah. All right, done. Large or very small numbers. Now, notice that when you're doing scientific notation, when you're doing scientific notation, it is always in the form a times 10 to the power of something. Okay, so it's changing a very large number or a very small number where you have a base a, and it's always times to the multiple of 10. But a has a restriction. A's can only be 1 to 10, but not including 10. So it's always a single digit. And, well, not a single digit, but it's within less than 10, sorry. And in the negative region, it can, same thing, it can only be 1 to negative 10, but not including negative 10. And M is write this in, an integer. What is an integer? Hands up if you know. What's an integer? Yes, Andrea? Very good. Integer is a negative or positive whole number. So if you think of any positive numbers or whole numbers, it can be both positive or negative. So the power cannot be decimal. The power cannot be a fraction. The power can be negative. So it can be negative or positive, but it has to be a whole number. That's what an integer is. Yeah? Now, let's take the example 15 million as a basic numeral. So when they say basic numeral, what they mean is write the number. So here, 15 million. How many zeros are there in 15 million? Can I please have, let's go with Olivia. 6, very good. So 1, 2, 3, so that's 15,000 times another 1,000. So you get another 3 zeros. That's 15 million there. So that's the basic numeral. That's relatively a small number when you have to write it. So if you're working in trillions, what you don't want to be doing is you don't want to be writing 15 and then, about 9 groups of zeros or 15 groups of zeros. There has to be a better way. So then we use what we call scientific notation to reduce the amount of zeros we have to write. And this is what we do. So in this chart, let's fill it in. This chart here, this is exactly 15 million. So I wrote 15 million. If I had to write it times by 10 to the power of something, this is what it will look like. It'll be 15 million. So that's 15 million times 10 to the power of what to make it still 15 million? 10 to the power of? Very good. This is 15 million times 10 to the power of 1, which means, actually no. Sorry, not 1. What do we need to change it to? Because if we times it by 10, it makes it now 150 million. How do I make it 1 though? 0, very good. So this should be 10 to the power of 0. Let me just fix that. 10 to the power of 0, so that is the same thing as saying 15 million times 1, which is still 15 million. What's the problem? Why is this not considered scientific notation? Joanne? Oh, I did too. What's that? 150. Oh, that's 150 million. That's not what I wanted. But that's okay. If it is this way, we can still fix it. So, if I want to write 150 million and I had 5, let's stick it with 15 million actually. Oh, this is why Eunice said 1. Oh, I get it now. Yes, then you're right. Times 10 to the power of 1. Sorry, I didn't see that was 150. It was meant to be 15 million to a point. So that's 15 million times 10 to the power of 1 will make it 150 million, which is true. Still going back to my point, why is this not a scientific notation? What's the problem?
Because it's not less than 10 and greater than 1.
Very good. Next time, hands up. So yes, this problem is 15 million. As an A value, it is not between the interval that we had already suggested. So whilst this is true, that's not how we would write it. If I wrote 15,000 or 1,500, what's wrong? All good? 1500? Who? Wait, shh, I can't hear it.
They stopped singing it.
Oh, did they? Thank you. Wait, let me pause the video. I'm going to record it.
Happy birthday to you. Happy birthday, dear Mr. Trout. Happy birthday to you.
Hip hip! And then we're going to delete as well. I see what I was trying to do. So 15 million is the number that you want. But you can have different bases. And what I was trying to do is to show you how it changes as you change the base number. So, yes, this was actually correct. It should have been 150 million. So 150 million, I'm just going to put the commas in so you can see. 150 million times, should have been times there by the way. But times 10 to the power of what to make it? 15 million. Joanne? Negative 1. And for those who aren't sure why negative 1, if you times by negative 1 using index law number 7, for those who've forgotten, index law number 7 says, if you times by negative power, it's the same thing as writing a to the power of m. What that's really saying is that's saying 10 to the power of negative 1 is the same thing as saying 1 over 10, which means you're dividing by 10. So 150 million times 10 to the negative 1 is the same thing as saying 150 million divided by 10, which makes it 15 million. Okay, so that sticks to the same value. So here, this will be equivalent to 150 million divided by 10, which equals 15 million. Okay? Next one. Part B, so I tried to change the base to still make the same idea. So I need 1500 times, how many zeros do I need to make 1500 15 million? 4 zeros. So that means it would be 10, or not 10, but 1, 2, 3, 4, 10,000 to have that 4 zeros. But then if you write this as a scientific notation, 1500 times 10 to the power of what to make 10,000? How do you write 10,000 in terms of tens? So 10 to the power of what? 4. So the number of zeros tells you what the power should be. Because 10 times 10 times 10 times 10, 4 times will give you 10,000. Let's go to the next one. If it's 150 and I want to times it to get to 15 million, I would times it to now. Notice I've lost 1 zero, so that means it needs to gain a 0 over here. And that would be what, Andrea? 100,000. 2, 3. And that has 5 zeros. So that means you would write 150 times 10 to the power of 5. All of this should all equal to 15 million. It's just different ways of writing 15 million, right? And hopefully by this point you start to pick up a pattern that I dropped another 10. So that means this now becomes 1 million. So 1, 2, 3, 1, 2, 3, 6 zeros. So 15 times 10 to the power of 6 is equivalent to 15 million. But again, all of these 4 examples, none of which fits the criteria that A needs to be between 1 and 10, not including 10. Okay? So that's why the last one is the correct scientific notation.
That's not the integers though. Oh, no, M is an integer.
M is an integer, but A can be between 1 and 10. So in this case, it'll be 1.5 times, and it would be 10 million. 1, 2, 3, 1, 2, 3. That's 7 zeros to make 15 million. So hence it's 1.5 times 10. Shh, thank you. Don't speak while I'm speaking. Thank you. And that right here, this is the correct notation for scientific notation. What you're going to be doing in this exercise is essentially to practice writing scientific notation, as well as in the next one I'm going to talk about significant figures. You see that number that we've worked here, that 1.5? You can round those numbers. So not every time it's always nice and it's 15. Sometimes they will say round this to 3 significant figures or 2 significant figures or 1 significant figure, and you still keep it in scientific notation. Okay, so it's just knowing what do you change the base to, and that's what the next part is. Significant figures is different to rounding. Significant figures are used to help us summarize things. So an example is, does anyone know how many people, what's the population of the world? Just out of curiosity. 8 billion.
It'll be like 8.2.
Well, okay, let's go with that as well. Now, if we actually really think about it, is it actually true that it works out nicely that it's actually 8.2? No. This is actually where we use listening. Thanks, team. Please don't speak while I'm speaking. Thanks. The 8 billion, the 8.2 is actually us using significant figures to round it off, because we know that it's not exactly 8 billion, but we're using the first significant figure of 1, to say, well, 8 is easier for people to understand. Rather than saying 8 billion, I don't know, 600 million, 200,000 and 500 and whatever it is, it's too specific. People are just happy to know it's roughly 8 billion. So significant figures focuses on certain digits. And that's why they say we either round it to the first, second, or third digit. It's the one that is a non-zero. So fill in this part here. I counted from left to right, starting at the first non-zero digit, because we're focused on what matters. Okay, we're looking at the number that matters the most. So in our case, it's the 8 that matters, not so much the numbers afterwards. But if you said 2 significant figures, you could say 8.2. If you said 3, then it could have been 8.23, for example. Okay? Let's have a look at the next one. So when using scientific notation, the digit to the left of the decimal point is the first significant figure. So for example, you currently have this number here, 20,190,000. Okay? If I wanted to round this to the first significant figure, that would be 2.019. Now, if you wrote that, 2.019, this is the proper scientific notation. That's how we do it. But you see, some of the questions might ask you, I only want 1 significant figure. If they only want 1 significant figure, so 1 fig, then your answer would be 2 times 10 to the power 7, because the first digit is all they care about. If they said 2 significant figures, then you would have said 2.0 times 10 to the power 7. If they said 3 significant figures, you would have wrote 2.01. In this case, we're actually writing the full thing, which is scientific notation. We'll write all 4 significant figures. So that's where the questions might change. They might say, start off by writing scientific notation. Next one is round it to 2 sig figs or 1 sig fig. So the one I wrote over here, this is 1 significant figure, but still scientific notation. Okay? So if I said 2 significant figures, this is what the answer would have been. 2.0 times 10 to the power 7, this is considered 2 significant figures. You're still using scientific notation, but it gives just a bit more detail, kind of like the 8.2, so it was 8 billion versus 8.2 billion.
So this is the current population of the world.
8, read it out. 8 billion, 200, and something, I can't see it. 211,682,000. That would be the proper number, and it's still going, but we round it off as 8.2. Okay, or 8. Very good. All right, next one. All right, so let's use that example. How many significant figures are there in question A? Can I please have, let's go with Sean. How many sig figs do you see in example A? There are 3. So the first non-zero digit, that's considered 1. That means the next ones are 2 and then 3. So this is considered 3 significant figures. Next one. How many significant figures are shown here? Now remember, you can write this in its proper number, so basic numeral. 10 to the power of negative 3 is the same thing as saying divide this by, or times it by 1 over,
10 to the power of 3.
which is 1,000. Very good. So it should be 1 over 10 to the power of 3 is 1,000. So if you take this number divided by 1,000, what do you get? You get 0.00181. Now just looking at that basic numeral, what is your number of significant figures? Obviously I'm making it more complicated than it should be.
3.
Yeah, it's still 3. Because it's a first non-zero digit is still here. This is still number 1. That's your first. That's your second. That's your third, which you can actually look at from the first base number. It tells you number of significant figures already. So this is also 3. Yes, Una?
Do you have to do all that math, or can you just count?
Yeah, you can just count from here. I'm only doing that to help you understand the difference, how we're translating from scientific notation to basic numeral to significant figures. So that way you can see it all. Okay? And then your last one. How many significant figures are shown in 461? Can I please have? Let's go with Olivia. There are 3. Okay, so it's always just about counting the numbers. And here, this is also 1, 2, 3. All right, let's do some examples together, team. Next question, example 1, first page. Let's go through. Write these numbers in scientific notation using 3 significant figures. So using 3 significant figures and scientific notation. Remember, scientific notation, the number has to be between 1 and 10. Have a think. What should the answer be? Can I please have, yes, Una?
7.937 to the power of 10.
Times 10 to the power of? 6. Okay. Let me tell you which parts are correct. This is correct. This is not correct. Where have we gone wrong? What's going on? Violet. Wait, shh. Sorry? Very good. This is 4 significants. That's considered 1. That's 2. That's 3. That's 4. So I should actually stop at the 3, but this is still wrong. Why? Very good. So that 7 matters. That 4th digit still works as the way you normally round. If it's 5 or more, then you need to round this one because it's closer to the 4th important number. So you only want 3 significant figures. It's really important that 3 is closer to 4. So we round that up to the next part. It should then be, sorry, I should write the 7 so people understand. So then it should be 7.94 times 10 to the power 6. Okay, so this is 3 significant figures, scientific notation to represent 7,937,200. Okay, let's try another one. This number. So this number is a bit smaller, but same thing. I want 3 significant figures in scientific notation. Remember, the base number has to be between 1 and 10. Who wants to have a go with this one? Hands up. Michelle.
2.71 times 10 to the power of 5.
All right, let's go. 2.71, so that's 3 sig figs, times 10 to the power of 5. Okay, let's have a look. Negative 5, very good. So this is correct. That's 3 significant figures. 10 to the power of 5, which is correct. There are 5 jumps. But if you times it, it would have been this way. And it would have been a larger number. So we need to go backwards. 2.7's over here. You actually need to go backwards. How many times? That's 1, 2, 3, 4 jumps actually. So it's not 5. It should be negative 4. So the answer, your final answer should be 2.71 times 10 to the power of negative 4. Because I'm moving backwards from 2.71. How do I go all the way back to 0.000271103? It's negative 4 jumps. Okay, starting to get the feel. Significant figures versus scientific notation. Flip over to the next page. And this is our last example. So this one, without using a calculator, you want to evaluate this. Now you can evaluate this using index laws. So here we go. Let's do this. You got, what number is that? That's 100, no, that's 1,800,000. So I'll put the commas in to be able to read. So you got 1,800,000 and you're dividing by 9 times 10 to the power 3. You got two ways to do this. One, you can write this as a basic numeral, so both of them as basic numerals, and then work it out from there. Or a quicker way, which is to practice your index laws, you can rewrite them all as scientific notation. This is already in scientific notation. So you got divide by 9 times 10 to the power 3. How do you write 1,800,000 as scientific notation? Can I please have... Let's go Samuel, have a go. How do you write this as scientific notation?
Just do 18 times 10 to the power of 5.
That is correct, except A, remember A has to be between 1 and 10? 1.8. So that, very good. So it should be 1.8 times 10 to the power of 6, and you're dividing that by 9 to the power of, times 10 to the power of 3. So how do you do this? If you write it out as a fraction, you can see it. It's 1.8 times 10 to the power of 6 all over 9 times 10 to the power of 3. Now, kind of like what Samuel was doing before, I think he was going ahead. That's why he said 18, which is not wrong. It actually makes your life easier. Can you see the bases? We can actually manipulate that number so that it works in our favor, because 18 and 9 would work really well. So maybe what Samuel did before was, instead of 1.8 times 10 to the power of 6, it was better to write it as 18 times 10 to the power of 5, which is still 1,800,000. And the bottom I'll still keep as 9 times 10 to the power of 3. Why do we do that? Because we can separate the numbers of numbers, bases of bases. Yeah, the way we've done it in index laws. So here, if I separate the two, you now have 18 over 9 times 10 over 10 to the power of 5 divided by 10 to the power of 3. You can use your index laws here. Index law number 2. Same bases, subtract the powers. So here, that should give you 18 divided by 9 is 2 times 10 to the power of 5 divided by 10 to the power of 3 gives you 10 to the power of 2. But 10 to the power of 2 is the same thing as saying 10 times 10. So it's 2 times 100, and your answer is 200. So you can see that we've done something without using a calculator, and we're essentially using index laws and scientific notation to get there. You can write 18, yeah. So this is where you do a bit of problem solving. Okay, so the first part's of the exercise to get you to work with scientific notation, but you want to manipulate it to get somewhere that you can solve. Let's try B. I'm going to pause the video. I'm going to give you, let's say, 3 minutes. See if you can do the second one in the same idea. Can you do it without a calculator and see if you can solve it? And that's got a few seconds left. Check your answers if you're already on it. Aims to get the 8. But the final answer should be 0.8. Oh, wait, did I do it wrong? Oh, I did it wrong, sorry. Oh, my bad, my bad. You were right. Oh, no, I was right. I was right. That is -3. Sorry, my bad. I saw this line and I was like, oh, why did it become a 3? My bad. Because 24 has to be -3. So I was right.
What the hell did he do? What? So what did you do? Isn't it -3?
It's -3. It's 0.8. All right, team. Let's review. Shh, shh, shh. Here we go. Eyes this towards the board. U9s. Thanks, U9s. Thank you. As you're doing this problem, the key step was right here. If you had 2.4 times 10 to the power of negative 2, that is correct in scientific notation. The goal, though, is to make it a whole number so you can work out 24 divided by 3. But if you make it 24, you're increasing this by 1 decimal. That means this has to go back by a decimal. So it should be 10 to the negative 3. And then separate them. 24 divided by 3 is 8. Negative 3 minus the negative 2 is negative 1. That's the same thing as saying divided by 10. So 8 divided by 10 is 0.8. Okay, I'm going to stop the video there and leave the notes here. But that's exercise 3C, working with scientific notation, significant figures, and index laws. I'm going to pause the video. I'll finish the video.